Hi, good day. Today, again, we will be discussing one of our feedback and control assessment lab finals, and this is the LA203. So the question is, a system with the block diagram shown below has a transfer function of Fs is equals to 1, Hs is equals to 1, Gs is equals to 1 over S plus 4 times S plus 5 times S plus 15 times S plus 20. Okay. So the first question is, characterize the performance of the system if the compensator, the CS, which is given here, is a pure gain and is set to a value so that the dominant complex poles has a 25% overshoot. Summarize the performance of this uncompensated system in a table and present the response plot. Okay, so since the given transfer function is GS, we will actually use this as the first procedure for this question. So plot the system transfer function 1, and you have this transfer function, you will end up with this transfer function. So using the CISO tool is where you can edit the architecture of the transfer function, the continuous transfer function. And if I will show you how it's done, okay, as you can see here, I will copy and paste this system transfer function here. Just enter. You can see the continuous transfer function and plotting the CISO tool for the system. You can see it will go through the control system designer, and remember the plot that is shown, you can see it here in the edit architecture. And also another fact is you can see the transfer step signal, the step response, the root locus editor for loop transfer, and the Bode editor for loop transfer, the Bode. And when clicking the edit architecture, you can see the given system in the question earlier, and you can see the block names, which is given right here, and you can also change the block names by entering it in the command window. So for this question, I had managed to show you all of the step response, the root locus, and the Bode plot for this system. So again, as I mentioned, going to the edit architecture to check the given transfer function, we had to input all of the values as stated on the question here. This is the values, so that it could work through the system. Since the system has no values yet, we had to overwrite the values so it could run. So pressing our locus system, this will show. Okay. So if I had managed to enter this will show us the given root locus. And by focusing on the 25% overshoot, as I had managed to make it 24.6, which is, if rounded up, we will get a 25% overshoot. We have a negative 2.5 plus 583 and 1 I, and a dumping ratio of 0.408. Writing this script on the command window, we could see it here that it's converted to a CLG and continuous time transfer function. So again, using the CISO tool for the architecture, so that we could change the value of a given system. We will end up having this step response showing that it has a time of 0.63 seconds and an amplitude of 0.780. So, letter B, designing an ideal derivative compensator to hasten the peak time by a third from the uncompensated system. So again, as you can see, we had this value of 1.02 plus E04. This is given in one of our plots here. As you can see, it's the gain. It's given in the gain. I had used it for the letter B for this question, and having a C of 0.44568, and going for the R locus and the CISO tool, we will end up having a C on, we will end up having this graph right here. Okay, so this is, and changing the C, we will just change the C of the value given here, since we will be designing an ideal derivative compensator. Changing the C, this is remember, this is a PIPD compensator. Changing the C for this, we will be having this root locus for this equation, and also for the root locus, as I had mentioned earlier, for the edit architecture, you could always see the root locus, the step response, and the Bode editor. So don't forget to press the arrow right here, and after you press, look for the C section. This C, if you were to plot the C, you have to write also the C in this section, this arrow right here. Click OK and then apply to C so that it could read for the architecture. It will compile the architecture, and it will show the values of the root locus, the step response, and the Bode plot. So design now a ideal integral compensator cascaded with a PD compensated. The PD compensated here is what I've used. So to reduce the step response to 0. So summarizing the performance of the uncompensated and PID compensated system. Note this is now a PID compensated system. As you can see, I had also again used the transfer function of 1.02. This is the gain earlier for my earlier root locus as shown here. So using the gain of it and getting 0.48772, which is much closer for the PD compensator. So the R locus is G and the CISO tool is G. As you can see, the CISO tool, don't forget to edit the architecture, overriding the C section, clicking the arrow down and clicking to apply for it to work. This is the root locus. As you see, there is no much difference for the letter B part. But if you could see the Bode editor for the loop transfer, you can see that it's different from the letter B, the PD compensator, which is, this is a PID overridden with a PD compensator, which is it's cascaded between the PD compensator, but since this is a ideal integral compensator, it's different. As you can see here, this is 54.9 degrees, and for the PD compensator, it's at 62.3 degrees. Okay, so that would be all of my answers. Thank you much for listening. Have a great day.